Welcome back, and in this short topic we're going to be looking at shape of molecules. Shape is very important, especially within biochemistry. If you change the shape, you change the function. Quite a lot of proteins work on this idea of a lock and a key mechanism. So we can activate the protein or deactivate the protein by changing the subtle shape. So we can predict the shape of simple molecules using something called the electron pair repulsion theory. Sometimes this is known as VESPR, the valence shell electron pair repulsion theory. And there are two key principles to this one. The first one states that the bonding pairs of electrons around a central atom repel each other and arrange themselves as far apart around that central atom to minimize repulsion. Sometimes we say maximize separation. Notice it is the bonding pairs of electrons. We're not talking about all the electrons here, only the bonding pairs around the central atom. They repel each other and remain as far apart as possible, so they minimize repulsion or maximize separation. So they get as far away from each other as possible. Key thing, as I said, is to remember it is only the bonding pair, the outer shell. That's why it's sometimes called the valence shell electron pair repulsion theory. So let's look at an example of how we can work this out. We're going to look at the shape of methane, CH4. So the first thing I'm going to do is I'm going to do a dot cross diagram showing outer shell electrons only. So CH4, you've got one carbon and 4 hydrogens covalently bonded, and there's a single covalent bond between each hydrogen and the carbon, and there are no lone pairs. So we say that there are 4 sigma bonded pairs. Another way of saying this is I've got 4 areas of electron density. I've got no lone pairs, therefore my total is 4. So the electron pair arrangement is something called tetrahedral. And you will have to learn those. So you do need to know the electron pair arrangement and the shape of the molecules. Now, because there are no lone pairs, my electron pair arrangement and my shape are the same. So in this case, the shape is also tetrahedral. We'll come on to some examples when these two are not the same, and that's where we have lone pairs. Now we have to think about drawing the 3D shape. So to try and demonstrate this on a flat piece of paper, I'm going to use certain conventions. So there's 2 hydrogens with the straight lines, they are in the plane of the paper. Then I use a wedge to show that one hydrogen is coming out towards me, and a dotted line to show that there is one hydrogen going away from me. Now the bond angle is the angle between the 2 covalent bonds. So in this case, all the bond angles are the same, so it's the bond angle between these 2 covalent bonds, and in this structure it's 109.5. In other words, that's the furthest these bonding pairs of electrons can get away from each other. I'm going to do the same process on the next page. So BeCl2, beryllium dichloride, has 2 sigma bonding pairs around the beryllium, and it has a linear shape. So there's a 180 bond angle. BeCl3, 3 sigma bonding pairs. This time the shape is trigonal planar. Notice in these two there are no wedges and no dotted lines, and that's because these are both flat molecules. In other words, they don't have any sticking out bits. They are planar. We've come across the tetrahedral shape before. It doesn't matter what the atoms are. If there are 4 bonding pairs and no lone pairs, you are going to get a tetrahedral arrangement, irrespective of what atoms I'm actually dealing with here, and they will have a bond angle of 109.5. The last 2 are a little more complex. So we have 5 sigma bonding pairs. We have PCl5, and this is one of the strange ones where it has 2 different bonding angles. So it has this kind of planar arrangement, this trigonal planar, but then it has the 2 chlorines above and below the plane of the molecule, and this is called Trigonal Bipyramidal. So there's a 90-degree bond angle between the 2 upright ones and the planar part around the middle, and then we have the normal 120 bond angle around the 3 groups in the middle. Last but not least, we have SF6 with 6 bonding pairs, and this is an octahedral with bond angles at 90 degrees. Notice we've got 2 coming out towards us, 2 going behind, and then the 2 fluorines above and below the plane of the molecule. And this is called octahedral because it has 8 faces. So the first rule states that bonding pairs of electrons repel each other to maximize separation or to minimize repulsion. The second rule deals with lone pairs. Now, lone pairs are held more closely to the central atom. They exert a greater repelling effect than bonding pairs. So lone pair repulsion. So lone pair repulsion is greater than lone pair bonding pair repulsion, which is greater than bonding pair repulsion. So if you've got 2 lone pairs, they're going to repel more than a lone pair and a bonding pair, but the lone pair and the bonding pair are going to repel more than the bonding pair. And basically every lone pair reduces the bond angle by approximately 2 per lone pair. We're going to see that in action. So the first one we're going to look at is SO2. It has 2 sigma bonding pairs. Notice they're double bonds, but because you've got only 2 areas of electron density, I'm only counting it as 2. But they do have 1 lone pair, which makes a total of 3, and an electron pair arrangement is trigonal planar. But because of the presence of the lone pair, that is not now the shape. The shape in this case, well, we have a sulfur double bond to the 2 oxygens, but because that lone pair is there and it requires a greater repelling effect, you would expect normally, if this was a trigonal planar molecule, that this bond angle here would be 120. It's not, it's been reduced to 118, and we call this a bent shape. Ammonia is the next one we're looking at. This has 3 sigma bonding pairs, 1 lone pair, so it makes a total of 4. So its arrangement is based on tetrahedral. But again, because of the presence of the lone pair, that is not the shape. So you can have your nitrogen with your lone pair, and it has your 3 hydrogens, which are arranged like this. So 1 in the plane of the paper, 1 coming out towards you and 1 behind. And this time you've got a shape trigonal, because there's 3 of them, pyramidal, because it looks like a pyramid. Notice I generally speaking draw the lone pair on the top, and again, because this was tetrahedral, you'd expect it to have a bond angle of 109.5. Because that lone pair has that greater repelling effect, you've reduced the bond angle to 107. The next example is water with 2 bonding pairs, 2 lone pairs again, therefore it's based on a tetrahedral electron arrangement. But water has 2 hydrogens and it has 2 lone pairs of electrons. So the shape again is bent, and the bond angle now is 104.5. Again, we've reduced the bond angle because these lone pair repulsion is greater than lone pair bonding pair repulsion, which is greater than bonding pair repulsion. Next one on our list, SF4. SF4, 4 bonding pairs, 1 lone pair, 5. So it's based on trigonal bipyramidal. It's a little bit of a difficult one. We call it Seesaw, and it's got quite a wide range of bond angles, so we don't tend to talk about the bond angles in this one. So you've got kind of your things here, and then try to draw this, an F and an F, and that's a seesaw, because this acts as your kind of fulcrum, and then these are the 2 bits of your seesaw. Next one, still based on trigonal bipyramidal with a 3 and a 2 arrangement. Now there are 2 possible shapes that this compound could adopt. One is T shape, where you've got your 2 lone pairs on your iodine, and then you've got your Cl in a kind of a triangle arrangement, and this is T-shape, or you've got your iodine here with your lone pairs above and below, if you like, the plane of the molecule, and then you've got Cl, and then you've got dotted Cl, and then you have a wedge, Cl, and this is either trigonal planar, which would be this molecule, or T-shape, which would be that molecule. Now, the reason that certain molecules adopt certain shapes is a bit beyond this topic. The next one is based on an octahedral shape. So we have your iodine in this case. Again, one lone pair, and then you have one F pointing, if you like, down, could do up if you want to. And then again, we've got kind of a square shape around the iodine. So this is square pyramidal. Oopsie, sorry, P middle. In other words, looks like a pyramid but with a square base. Last but not least, we have XeF4. So Xe, lone pairs above and below the plane of the molecule, and then you have basically a square shape like so. See, F, and obviously because it looks like a square, it is a square, it's called square planar. And you need to learn all of those.